Good day, ladies and gentlemen. This is our third discussion for Physical Sciences, Grade 12, Term 2. And we are going to look at an example right now about the work energy theorem. Now, the first example is a relatively easy one. Now, the question is that we need to determine the speed of an object after it's moved 20 meters. We assume that the object started at rest. That means the initial velocity is equal to 0. And the net work done by the object over this distance of 20 meters is going to be 3730 joules. Now, the object that we are talking about has a mass of 40 kg. Now, the best way to do these, or any calculation really, is to first take out what you have. I have briefly summarized this here now, but we can say that the mass of the object is 40 kg. The initial velocity is 0 because we say it started at rest. The final velocity is what we need to determine. We know it traveled 20 meters, so our displacement in x is 20 meters, and the work that was done is 3730 joules. Now, as it stands, we need to choose the correct formula. In the previous video, I did mention that you need to make a concerted effort to familiarize yourself with the formula. This is so that when you look at this, when you know the things that you have and the things that you need, you can choose the appropriate formula. In this instance, we are going to use work net is equal to delta EK, which we can of course write as half mass velocity final squared minus half mass velocity initial squared. Now, first thing we do, we check our formula. Does this formula have a velocity initial? Yes. Velocity final? Yes, that's what we want. Does it have mass? Yes, it does. Does it have a net work? Yes, it does. It doesn't have anything with displacement though, but that does not matter because this formula has an unknown that we want, and all the other things are knowns. So we can say work net is equal to half mass velocity final squared minus half mass velocity initial squared. We substitute the work net for 3730 joule. We then have half of 40 kg and our velocity final squared minus half our mass 40 and our initial velocity, which was 0 because we started at rest. Now this gives us a formula, or an equation rather, with only one unknown, and that is something that should be relatively easy to solve. Just bear in mind that if you were to rearrange this formula to get velocity final squared on the one side with everything else on the other side, to actually get your velocity final, you need to do the square root. Do not forget about that when doing your final answer. And this actually, if you were to calculate this, unless I made some mistake, gives us 13.66 meters per second, which you can round to 13.7 meters per second. On the subject of rounding numbers, as a general rule, you always go to 2 decimal places unless specifically stated otherwise. And if you do what I have done and you round this to 13.7, you still write 13.66 before you write 13.7. You do not leave out any steps, which is exactly what I did over here. But for the sake of explanation, I'm trying to save some time for you guys. Now, we can do another example, a somewhat more complicated example. For this one, let us say that we have a trolley on an incline. Okay, I'm not much of an artist, but I try. And this trolley has a mass of 2 kgs. It is initially at rest at the bottom of this ramp and is pulled up at a uniform, or the ramp is uniform anyway, 25 degrees. And the force it is being pulled up with is 100 newtons. The entire distance, the displacement, is 8 meters. The trolley experiences a frictional force of 50 newton. Now, again, I've sort of read out and abbreviated the question for you. So let's start by taking out everything that we have. We have the mass of the trolley being 2 kg. It is initially at rest, so VI is equal to 0. It is pulled up the runway, which is 25 degrees, so our theta is 25 degrees. It has a constant force, so the force it is being pulled at is 100 newtons. It travels a distance of 8 meters, so our delta x is 8 meters. And the trolley experiences a frictional force, so friction is equal to 50 newtons. Now, that's everything we have before we've actually even looked at the question. Now, the questions that we have is to determine the net work done by the trolley. So number 1, we want the net work. Number 2, determine the velocity of the trolley. Now, we can do this in a few different ways, but I'm going to show you the more simple method of doing this. If we want the net work of the object, then all we need to do, the net work, is we need to first have a look at the parallel components of this force. Now, because what we have here is we have an incline, this force is not going to be perfectly for us to use the way it is here. The parallel component of our force, as you should know from previous work, is the mass and gravity, because this represents the force, sine theta. This should look familiar to you. The perpendicular component is equal to, again, mg cos theta. Now, if we go from this, we of course have the mass of the trolley, and G is always 9.8. We have theta, so these are actually formula that we can use. Okay, that is already a first step to getting the answer. Now moving on from this, you can say that the net force acting on this block is equal to the force plus the friction plus this component, our parallel component of the force. So that then becomes F plus F friction plus the F, the parallel component of gravity, which we of course write as F plus F friction plus mg sine theta. Now this leaves us with a formula that we actually have things to substitute in. We know the force is 100. We know that friction is 50 Newton. But because friction is in the opposite direction, we put a negative symbol in front of it because we are using that to indicate direction. It is acting opposite to our force. And then we of course have our final bit, mg sine theta. We know what the mass is, so that is going to be 2 kg. We know what g is, 9.8, and it is sine theta, which is 25 degrees. Unless I have again made a mistake, then that should give you a positive answer, first of all, of 41.72 newtons. So the net force acting on this block, the force pushing it up the incline, is 41.7 newtons. Now that's not the answer we wanted. We wanted work. But we also know that net work is equal to our net force, delta x, cos theta. Now, this is something that we spoke about in our previous discussion when we had a look at the positive and negative forces, or the positive and negative work, rather, apologies. So, what we have here is we have a net work is equal to a force. This force we have just calculated. We have a delta x, which we had in our first example. And now we have this cos theta. So at the moment, as things stand right now, we can substitute 41.72, I apologize, that should be a bracket, and 8. But what are we going to do for this cos theta? Now, for our example that we had previously when we discussed the idea of positive or negative work, we said that if you have your Cartesian planes and if the displacement or direction is between 0 to 90 or from 270 to 360, that's positive work. In this instance, we have positive work occurring, and cos in these two quadrants is equal to 1. In these two quadrants, it's equal to minus 1. Now, we have a theta of 27 degrees, 25, I apologize. So 25 degrees is going to be there, which is very obvious in our first quadrant, positive work. So we are going to use cos as 1. Or we can say cos 0 degrees. It actually makes no real difference, because all we want is we want this cos theta to give us an indication of where we are at in our Cartesian planes. So this becomes a 1. So our formula is 41.72 times 8 times plus 1. And that gives us a work of 333.73 joules. And we use a positive symbol to indicate that it is positive work being done. Now, the final part of our question, or rather the second part, was to determine the velocity. This we can do relatively easy with our work energy theorem that we spoke about previously. We know that the net work is equal to delta EK. Delta EK we know is equal to our EK final minus EK initial, which we know is equal to half mass velocity final squared minus half mass velocity initial squared. This again puts us in the position where we have a formula with everything we need to substitute. Work net. We just calculated the net work in our previous question, so we can say 333.73 is equal to half 2 kgs times our velocity final squared minus half times 2 kg, and we are again in a position, because the block was initially at rest, our initial velocity is going to be 0, and that puts us in the same situation we had when we did our previous calculations, where we only have one unknown factor. And that leaves us with our velocity final being 18.27 meters per second. Now, ladies and gentlemen, these calculations can be somewhat tricky sometimes, and sometimes you will find that they are asked in a manner specifically to confuse you. If you have any difficulty finding solutions or getting the answers I found, or you would like some extra examples, you are of course welcome to contact me, even though I am actually a biologist by trade, not so much a physicist. I will do my utmost best to help you. Ladies and gentlemen, next time we'll talk about the conservation of energy, conservative and non-conservative forces. Until then, have a nice day.